Hi, I'm Jan from Ralph Allen School. Today I'm going to talk to you about Hubble's law. By the end of this video, you should know pretty much everything there is to know. Now before we actually start explaining what Hubble's law is, I think we should say what Hubble's law states. Now Hubble's law states that all objects moving away from each other, the apparent relative velocity of these is proportional to the distance they cover. Okay, so I've prepared this balloon to show, to have visual aids to show Hubble's law. Now on this balloon I've drawn different galaxies on them. Here, 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 and here, and here. Okay, so these galaxies, as I blow this balloon up, they'll move further and further away from each other. This is exactly what Hubble's law is. Well, demonstrated on a balloon, of course. As you can see, the galaxies have moved further away from each other. Because imagine the balloon as space-time and the galaxies just stay where they are. It's not the galaxies moving away from each other physically, but it's space-time expanding and causing this effect. So if I blow it up even a bit more, you'll see a more greater difference. Alright, this is as much as I can blow up the balloon now, and you can clearly see the differences in the distances between the galaxies. Between the very small size, which was here, and what it was before. Okay, so you're probably wondering, if galaxies can move further from each other because space-time is expanding, how come particles don't move apart from each other? Well, it's kind of like this. So imagine this is the particle, and that's the nucleus, and these are the electrons. Now in between these, there's an intermolecular force of attraction. Now this force keeps the particles together, just like when you're walking your dog. When you walk your dog, there's a leash holding you and your dog together, right? So basically you can imagine this as a leash. That's why solar systems don't break apart. That just as in the solar system, there's gravity holding it together from the sun. That's why they don't move apart from each other. And because galaxies, they do have some form of attraction, but because they're too far, it's too weak for it to hold together, and that's why as space-time expands, this part gets further and further away from each other. And that's why really that's why only galaxies move apart from each other, not solar systems or particles or you from your dog. It's just like with the galaxies. If you're not holding on to your dog's leash strong enough, then if you're just holding it very weakly and the dog wants to move away, then it's going to run off. Isn't it? Okay, so I'm going to show you how Edwin Hubble had found out this occurrence. So, Edwin Hubble had realized that between us and the further galaxies, he saw that, I'm going to say this is Earth, he had seen that the galaxies were turning red. This is Earth, and let's say this is a distant galaxy. He saw that at first when the galaxy was emitting blue light, it was very high wavelengths, and it was a high frequency and high wavelength, so that would show the color blue. And then it turned green, which is kind of in the middle. and so it showed green. And then the final stage, by the time it came to us, it became a very long wavelength and low frequency of the color red. So from our eyes, the galaxy had turned red. And this only occurs when things move further away from each other. It's just like the Doppler effect. The Doppler effect is, for example, if you're on the street and a car goes past you, you know it makes that sound like meow. Now that sound is showing that that you're the subject, and the thing moving, its wavelengths get higher and higher and then shorter and shorter, because you can hear it at different places, and it takes sound longer to get to your ears. It's just like this, except with light. So when light objects get further away from you at a very fast speed, then it'll make this pattern, as I said. It'll go from a very high frequency to a lower and even lower until it becomes red. And of course, this is us, the subject. This is us. And that's just how we see it, because of the red shift occurring with the Doppler effect in the electromagnetic spectrum. So now I'm going to show you how to work out equations using Hubble's law. Now this equation shows how fast galaxies or objects in space move away from each other at what speed. Now v is obviously velocity. The h is Hubble's constant. Well, Hubble's constant isn't really very constant because it changes all the time. Well, not all the time, but quite regularly. Now the 0 here shows the stage of the universe. So right now the 0 is represented as our stage of the universe right now. And d is the actual distance. Imagine you had an actual ruler and you measured out between the two objects. Now Hubble's constant is 70.6 kilometers per second per megaparsec. 1 megaparsec is 3.3 light years. Okay, so now I'm going to show you how to solve equations using Hubble's law. Now, as I said before, Hubble's law was velocity equals Hubble's constant times the distance. Now, right now, remember, we're going to work out the apparent relative velocity, as Hubble's law states that the apparent relative velocity is proportional to the distance, and so as things get further away from us, they seem to go faster. So I'm going to draw two galaxies over here. Right here. There's two galaxies. And between them, let's say that there's 5 million kilometers. Okay, so let's use Hubble's law, which is velocity equals Hubble's constant, which is 70.6 kilometers per second per megaparsecs. So it's 70.6 times 5 million. So therefore velocity equals, let's get our calculator out, 70.6 times 5 million equals 353 million. 353 million. Now that's a very large number. So it's moving at 353 million kilometers per second per megaparsec. So basically it's moving 353 million kilometers per second per 3.3 light years. Thank you for watching. I hope you understand Hubble's law now. Bye.